The first sign will not be panic. It will not be empty shelves or people fighting over the last remaining goods. It will be silence, products you once reached for without thinking simply no longer there, replaced by gaps, substitutions, or nothing at all. No announcement, no warning, just absence. And by the time most people notice, the system that once made those items abundant will already be under strain. What disappears first is not random. It follows patterns, economic, logistical, chemical, and deeply interconnected. And once you understand those patterns, you begin to see something far more concerning than temporary shortages. You begin to see structural fragility. The danger is not that 10 items are disappearing. The danger is that these items represent pressure points, critical nodes in a vast supply network optimized for efficiency, not resilience. Modern retail shelves, especially across the United States, operate on what is known as just-in-time inventory systems. This means products are not stored in large backroom reserves, but continuously replenished based on real-time demand forecasts. It reduces cost, increases profit margins, and keeps goods fresh. But it also removes buffers. When disruption occurs, whether from raw material shortages, transportation bottlenecks, or energy fluctuations, the system does not bend, it stalls. One of the first categories quietly vanishing is low-cost processed food staples. Not because people are buying more, but because manufacturers are producing less. The misunderstanding here is simple. Consumers assume if demand exists, supply will follow. But production decisions are not based solely on demand, they are based on margin. Many inexpensive processed foods rely on complex ingredient chains, including emulsifiers, preservatives, and stabilizers derived from petrochemicals. When energy prices fluctuate or chemical production slows, these inputs become expensive or scarce. Companies then face a decision: raise prices on low-margin goods or discontinue them entirely. Increasingly, they choose the latter. The hidden science behind this lies in industrial chemistry and scale economics. A single processed food product might rely on dozens of microingredients sourced globally. Even a minor disruption in one component, such as a specific food-grade acid or thickening agent, can halt production. Unlike raw commodities, these specialized compounds are produced in limited facilities, often overseas. If a plant shuts down or redirects output, the ripple effect spreads quickly. Evidence of this has already appeared in sporadic shortages of packaged snacks, instant meals, and budget grocery brands. Not dramatic enough to make headlines, but consistent enough to signal a trend. The survival implications are subtle but significant. These foods are not just conveniences, they are calorie-dense, shelf-stable, and accessible to lower-income populations. As they disappear, people are forced to shift toward alternatives that are either more expensive or less durable. This increases financial strain and reduces food security, especially in urban environments where fresh food access is already limited. The system begins to favor those who can absorb cost increases, leaving others exposed. As this pressure builds, the next category begins to thin: affordable protein sources, particularly canned meats and certain dairy products. At first glance, this seems counterintuitive. Protein is a staple, a priority. But the production of animal-based protein is one of the most resource-intensive processes in the food system. It requires feed, water, land, transportation, refrigeration, and strict regulatory compliance. When any part of this chain tightens, such as rising feed costs due to grain shortages or transportation delays caused by fuel volatility, the entire system becomes less efficient. Misunderstanding here is that shortages are caused by lack of animals. In reality, they are caused by processing limitations. Livestock may exist, but if processing plants reduce capacity due to labor shortages, energy costs, or regulatory pressures, supply cannot reach the shelves. This creates a paradox where supply exists upstream but disappears downstream. The hidden science involves thermodynamics and logistics. Meat processing and storage require continuous cold chain integrity. Even a brief interruption in refrigeration can render large quantities unusable. Maintaining that cold chain is energy intensive, and as energy costs rise or infrastructure becomes strained, maintaining consistent output becomes increasingly difficult. Evidence of this has already emerged in fluctuating availability of certain dairy products and canned proteins in various regions. Not complete absence, but inconsistency, brands rotating out, sizes shrinking, prices creeping upward. These are early indicators of a system adjusting under pressure. The survival implications are immediate. Protein is essential for maintaining muscle mass, immune function, and overall health. As access becomes less predictable, nutritional stability declines, particularly for those without the means to diversify their diet. This leads to escalation. As protein becomes less accessible, demand shifts toward plant-based alternatives and shelf-stable substitutes. But these alternatives rely on their own complex supply chains, often involving imported ingredients, specialized processing, and high-energy input. The system does not stabilize, it transfers stress from one node to another. And as this happens, another category begins to quietly disappear: basic hygiene products. At first, this seems unrelated, but the connection lies in shared raw materials and manufacturing infrastructure. Many hygiene products, such as soaps, detergents, and paper goods, depend on the same chemical supply chains as processed foods. Surfactants, bleaching agents, and packaging materials all originate from industrial chemical processes tied to energy markets. When production prioritizes higher margin industrial contracts, consumer grade goods become secondary. The misunderstanding is that these items are simple and easy to produce. In reality, they are the result of highly optimized industrial systems designed for scale. A disruption in pulp production affects paper towels and toilet paper. A shortage of specific surfactants affects detergents and cleaning agents. The hidden science here involves material science and process engineering. These products require precise formulations and manufacturing conditions. Substituting ingredients is not always straightforward, especially when safety and regulatory standards are involved. Evidence has already been observed in periodic shortages and reduced variety in cleaning products and paper goods. Again, not total collapse but a narrowing of options. The survival implications extend beyond convenience. Hygiene is a critical component of disease prevention. Reduced access to effective cleaning products increases the risk of infection, particularly in densely populated areas. As these layers of pressure accumulate, the system begins to exhibit a pattern: simplification, fewer product varieties, fewer brands, fewer options. This is not a temporary adjustment, it is a structural response to sustained stress. Companies streamline operations to focus on core products, eliminating those that are less profitable or more complex to produce. This leads to another category quietly fading from shelves: specialty medical and over-the-counter health items. These include niche medications, specific formulations, and less commonly used health products. The danger here is not immediate for the majority but critical for those who rely on them. The misunderstanding is that pharmaceutical supply chains are robust and insulated. In reality, they are highly globalized and dependent on a small number of manufacturing hubs for active pharmaceutical ingredients. When disruptions occur, whether from geopolitical tensions, regulatory changes, or production issues, the impact can be widespread. The hidden science involves pharmaceutical chemistry and regulatory compliance. Producing a medication is not just about mixing compounds, it requires strict adherence to quality standards, testing, and certification. Scaling production up or down is not instantaneous. If a manufacturer exits a market due to low profitability, replacing that supply can take months or years. Evidence of this has already been seen in intermittent shortages of certain medications and medical supplies across the United States. The survival implications are profound. Health becomes less predictable. Conditions that were once easily managed become more difficult to treat. This increases the burden on healthcare systems and individuals alike. And as this pressure mounts, the system continues to shift, revealing deeper vulnerabilities. Because what disappears next is not just a product, it is a capability. And when capabilities begin to vanish, recovery becomes exponentially more difficult. What disappears next is not something most people ever consciously notice, because it has always been there, silent, reliable, and assumed. It is the category of components, the invisible backbone of modern manufacturing: small electronics, replacement parts, and low-cost hardware items that keep everything else functioning. The danger is not in their absence as standalone products, but in the cascading failures that follow when they are no longer available on demand. A missing fuse, a specific capacitor, a low-cost microcontroller — these are not items people stockpile. Yet without them, entire systems stall. The analysis begins with the structure of global electronics supply chains. Over the past 2 decades, production of semiconductors and electronic components has become geographically concentrated, with fabrication facilities clustered in a small number of regions. These facilities operate at extreme precision, requiring stable power, clean water, rare materials, and uninterrupted logistics. Even minor disruptions, whether from environmental stress, trade restrictions, or energy instability, can reduce output. Unlike other goods, electronic components cannot be easily substituted. A circuit designed for a specific chip cannot simply accept another without redesign. This rigidity creates a bottleneck that propagates across industries. The misunderstanding is that shortages only affect high-end devices, smartphones, computers, advanced machinery. In reality, the first signs appear in the lowest cost, least visible components. Manufacturers prioritize high-margin products when supply tightens, diverting limited resources toward items that generate the greatest return. This leaves low-cost components underproduced, even as demand remains constant. The hidden science here involves supply chain optimization algorithms and yield rates in semiconductor fabrication. Producing chips is not a linear process. It involves multiple stages where defects can occur. When yield drops, the total number of usable components decreases and allocation becomes strategic rather than equitable. Evidence of this pattern has already surfaced in delayed repairs, extended wait times for appliances, and reduced availability of basic electronics in retail stores. Automotive manufacturers, for example, have halted production lines not because of missing engines or steel, but because of a lack of specific microchips. The same principle applies to household goods. Washing machines, refrigerators, and even simple tools increasingly rely on embedded electronics. When those components are scarce, entire product lines disappear or become prohibitively expensive. The survival implications extend beyond inconvenience. Modern infrastructure depends on continuous maintenance. Water systems, power grids, transportation networks all require replacement parts to function. When those parts are delayed or unavailable, small failures accumulate. A pump that cannot be repaired leads to reduced water pressure. A control system that cannot be replaced leads to outages. These are not immediate collapses, but gradual degradations that compound over time. As this degradation spreads, the system responds by reallocating resources, prioritizing critical sectors while deprioritizing consumer access. This creates a widening gap between what exists and what is accessible. And within that gap, another category begins to fade: affordable clothing and textiles. At first, this seems unlikely. Clothing is ubiquitous, mass-produced, and relatively low-tech. But the reality is more complex. The global textile industry relies on a tightly coordinated network of raw material production, chemical processing, manufacturing, and transportation. Cotton, polyester, dyes, and finishing agents all originate from different parts of the world. When any link in this chain weakens, whether due to water scarcity affecting cotton yields, petrochemical fluctuations impacting synthetic fibers, or shipping disruptions delaying distribution, the entire system slows. The misunderstanding is that clothing shortages would only occur in extreme scenarios. In truth, the first signs are subtle: fewer options, lower quality, longer restock times. The hidden science involves resource intensity and environmental constraints. Cotton cultivation requires significant water and stable climate conditions. Synthetic fibers depend on petroleum derivatives. Dyeing and finishing processes require chemicals and energy. Each step introduces potential points of failure. When costs rise or inputs become scarce, manufacturers reduce output or shift to higher-margin products. Evidence can be seen in rising clothing prices, reduced durability of garments, and increased reliance on fast fashion cycles that prioritize speed over quality. The survival implications are often overlooked. Clothing is not just about comfort or appearance, it is protection. In extreme temperatures, inadequate clothing increases the risk of hypothermia or heat-related illness. Reduced access to durable textiles also impacts shelter construction, insulation, and repair capabilities. As clothing becomes less reliable, attention shifts to another foundational category: basic tools and repair equipment. These are the instruments that allow individuals to maintain, adapt, and survive in changing conditions. Hammers, screwdrivers, manual tools, these seem simple, but their production depends on steel, precision manufacturing, and distribution networks. When industrial output prioritizes large-scale infrastructure or high-demand sectors, small consumer tools become secondary. The misunderstanding is that tools are durable and once purchased, rarely need replacement. While partially true, tools wear out, break, or become insufficient for new challenges. The hidden science here involves material fatigue and manufacturing tolerances. Low-cost tools are often produced with minimal margins, relying on high-volume production to remain profitable. When material costs rise or production capacity decreases, these items are among the first to be reduced or discontinued. Evidence appears in limited availability of certain tool types, increased prices, and longer lead times for restocking. The survival implications are direct. Without tools, the ability to repair infrastructure, build shelters, or adapt to new conditions is severely constrained. This reduces resilience at both individual and community levels. As these constraints accumulate, the system undergoes another shift, this time affecting something even more fundamental: packaging. It is not the product itself, but the means by which it is stored, transported, and preserved. Glass bottles, aluminum cans, plastic containers, these materials are essential for maintaining product integrity and extending shelf life. When packaging becomes scarce or expensive, entire categories of goods become difficult to distribute. The misunderstanding is that packaging is secondary and afterthought. In reality, it is a critical component of the supply chain. The hidden science involves materials engineering and logistics. Packaging must meet specific criteria: durability, impermeability, weight efficiency, and cost-effectiveness. Producing these materials requires energy, raw inputs, and specialized manufacturing processes. Aluminum production, for example, is highly energy-intensive. Plastic production depends on petrochemical availability. Glass manufacturing requires high-temperature furnaces and continuous operation. Evidence of packaging constraints has already emerged in limited availability of certain beverage formats, reduced portion sizes, and shifts toward alternative packaging solutions. The survival implications are significant. Without effective packaging, food spoilage increases, transportation becomes less efficient, and waste rises. This reduces overall system efficiency and exacerbates shortages. At this stage, the pattern becomes undeniable. The disappearance of individual items is not isolated, it is interconnected. Each missing product represents a strain in a larger system, a signal that the balance between efficiency and resilience is shifting. And as that balance continues to tilt, the next category to quietly vanish is not something you can hold in your hand. It is time. Not in the abstract sense, but in the measurable operational sense that governs how systems function. Delivery times extend, repair times lengthen, production cycles slow. The assumption of immediacy, the expectation that anything can be obtained quickly, begins to erode. This is not a visible shortage, but a temporal one. The system still produces, still delivers, but at a pace that no longer matches demand. The misunderstanding is that delays are temporary, anomalies that will correct themselves. But when delays become consistent, they indicate a fundamental shift in system capacity. The hidden science involves throughput and queuing theory. Every system has a maximum rate at which it can process inputs and produce outputs. When demand approaches or exceeds this rate, delays increase exponentially. Small disruptions that were once absorbed now create backlogs that take longer to clear. Evidence is already present in extended shipping times, backordered products, and longer wait periods for services. The survival implications are profound. In a system where time delays increase, planning becomes more difficult. Emergency response is slow. Access to critical goods becomes less predictable. This increases vulnerability, particularly in situations that require rapid adaptation. And as time itself becomes constrained, the system enters a new phase, one where prioritization replaces abundance, where choices are no longer about preference but about necessity. And in that phase, the final category begins to disappear. Not because it cannot be produced, but because the system can no longer afford to provide it to everyone. What disappears last is not a product you can point to on a shelf. It is not a brand, a package, or a specific category. It is optionality, the quiet, invisible layer of choice that once defined modern consumption. The danger here is not immediate scarcity but the collapse of flexibility. Because when a system loses optionality, it loses its ability to absorb shock. And when that happens, even small disruptions begin to have outsized consequences. The analysis reveals a simple but deeply overlooked principle. Abundance is not just about volume, it is about redundancy. In a healthy system, multiple suppliers, multiple materials, and multiple pathways exist to achieve the same outcome. If one fails, another compensates. But over decades of optimization, redundancy has been systematically removed. Companies consolidated suppliers, standardized components, and streamlined logistics to reduce cost. The result was efficiency, measurable, profitable, and scalable, but the trade-off was fragility. The misunderstanding is that full shelves equal security. In reality, those shelves often represent a narrow pipeline operating at maximum capacity. When 10 brands of a product exist, they may all depend on the same raw material, the same processing facility, or the same transportation corridor. The diversity is superficial. The underlying system is singular. And when that singular system encounters stress, the illusion of choice disappears rapidly. The hidden science behind this lies in network theory and systemic risk. Highly optimized networks tend to become tightly coupled, meaning that components are interdependent and operate with minimal slack. This increases efficiency under normal conditions but amplifies failure under stress. A disruption in one node propagates quickly because there are no alternative pathways to reroute the flow. Evidence of this can be seen in past supply disruptions where entire categories of goods were affected simultaneously, despite appearing unrelated on the surface. As optionality declines, evidence begins to manifest in ways that are easy to dismiss. Fewer brands on shelves, limited sizes, standardized variations replacing niche options, products reformulated to use available ingredients rather than optimal ones. These are not random changes, they are signals of a system simplifying itself to survive. And while simplification increases short-term stability, it reduces long-term adaptability. The survival implications are subtle but critical. When choice disappears, so does the ability to tailor solutions to specific needs. A person with dietary restrictions may no longer find suitable food options. A household requiring a specific part or product may be forced to improvise. This increases friction in daily life, requiring more time, more effort, and more resources to achieve the same outcomes. Over time, this friction accumulates, reducing overall system efficiency and increasing stress on individuals. As this process continues, escalation becomes inevitable. The system begins to prioritize, not through policy or directive but through economics and logistics. High demand, high margin, and high necessity items continue to flow, while low demand or low margin goods quietly disappear. This creates a stratification of access. Those with greater financial resources can still obtain what they need, while others face increasing limitations. The system does not collapse, it narrows. And within that narrowing, a final transition occurs. The focus shifts from consumption to maintenance, from acquiring new products to preserving existing ones. This is the point at which the disappearance of items reveals its true impact, because the loss was never about the products themselves, it was about the capabilities they represented. When low-cost processed foods disappear, the capability lost is affordable calorie density. When protein sources fluctuate, the capability lost is nutritional stability. When hygiene products become inconsistent, the capability lost is disease prevention. When electronic components vanish, the capability lost is repair and continuity. When clothing and tools thin out, the capability lost is protection and adaptation. When packaging declines, the capability lost is preservation and distribution. And when time itself becomes constrained, the capability lost is responsiveness. Each disappearance is a reduction in system functionality. Each gap forces individuals and communities to compensate, to adapt, to find alternatives. And while adaptation is possible, it requires knowledge, preparation, and resources. Without these, the burden becomes overwhelming. The final misunderstanding is perhaps the most dangerous: the belief that systems will self-correct before reaching critical thresholds. While many systems do exhibit self-correcting behavior, they do so within limits. When stress exceeds those limits, corrections become slower, less effective, and sometimes impossible without external intervention. The hidden science here involves nonlinear dynamics and tipping points. Systems can appear stable until they reach a threshold, after which change accelerates rapidly and unpredictably. Evidence of approaching thresholds is rarely dramatic. It appears as consistency in inconsistency. Repeated delays, persistent shortages, gradual price increases. These are not isolated events, they are patterns, and patterns, when observed over time, reveal trajectory. The survival implication is not to anticipate collapse, but to recognize constraint, to understand that the environment is changing from one of abundance to one of limitation. And in such an environment, strategies must shift accordingly. Efficiency at the individual level becomes less about speed and more about resilience. Stockpiling becomes less about quantity and more about diversity. Skills become more valuable than products. Maintenance becomes more critical than replacement. Because in the end, what disappears from store shelves is only the surface expression of a deeper transformation. A system that once prioritized availability is beginning to prioritize sustainability under constraint. And that transition, while gradual, is irreversible once it reaches a certain point. The shelves will not go empty all at once. They will become quieter, simpler, more predictable, but in a way that reflects limitation rather than abundance. And those who recognize the pattern early will not panic, they will adjust. They will understand that survival is not about reacting to absence but about preparing for it before it becomes visible. Because by the time most people see what is missing, the system has already moved on without it.